The device that we are building is called the IFMOC, Instrumented Fetal Membrane on a Chip device. Well, the device is designed to show disruption of cell-cell interactions that are associated with the integrity of the tissue. And so we really designed our studies based on cell-cell communication models that had used stromal fibroblast and epithelial cells in the presence or absence of toxicants as our core model. So we really designed everything around those studies. The risk for preterm birth occurs when tissue stability is lost, and it usually starts with premature rupture of the membranes, for example. There's been a huge amount of effort to try to reduce the incidence of preterm birth over the last 10 to 20 years, and very little progress has really been made. And this continues to be a problem for many women around the world. So our group had data that suggested that an exposure to a toxicant in an animal model unexpectedly caused the animals to have a higher risk of infertility and preterm birth if the animals were subsequently exposed to an infectious agent. It seems to be that the background environmental toxin exposure really impacts the likelihood that a common infection would affect that particular pregnancy. And so I think by using the devices to understand what we would call a second hit hypothesis has been really among the most fruitful things that we've been able to look at. And so we're very hopeful that that understanding would provide information to the physicians that are taking care of women at risk for preterm birth using a perspective that they haven't necessarily had in the past. Because of the difficulty in determining when people are exposed to toxicants versus when they become pregnant, when they might have an infection or not, we realized that really a background exposure to a toxicant might actually change a person's risk of delivering preterm. And so we felt like the environmental exposure history might be that missing piece. Everybody has a mother. Everybody has an experience from their time that they spent in utero, and we all are going to have a health consequence of one kind or another from that. The largest problem that is faced by the risk of preterm birth right now is that the women who exhibit this risk usually exhibit it during pregnancy. Our work that we have done from our animal models and our devices continue to confirm that really you need to understand this risk prior to the initiation of pregnancy, for one, and that we have been able to demonstrate that certain nutritional agents can be used to counteract the negative influence of some of the toxicants we study. And so in order to understand how cells communicate, you usually set up transwells with co-culture models. And these are still static cultures separated by membranes, but it's not a real-time experiment. So you really don't know how the cells might be responding to things they were exposed to at different time points. I think the organ-on-a-chip models in general allow us to study an in vivo-like microenvironment that's just not possible with static cell cultures that have been traditionally used by us and others. The device has verified some of our previous findings in the mouse model, which was really what we were hoping to see as something similar to what we had seen in vivo in the mouse. And it certainly also duplicated the work that we had done from the co-culture model, in which we knew that the presence of an epithelial cell type in concert with the stromal cell type allowed us to see changes in steroid-responsive biochemical agents that are necessary for sustaining pregnancy. Because the device can be examined microscopically, we can also look at signs of morphological differentiation. And so we have both morphological and biochemical parameters that we can easily monitor in the device. The device itself can be designed to read the progesterone responsive genes and proteins that we know are there. We're able to also monitor changes in receptor levels of progesterone, which have been linked to a risk of preterm birth. And so the cultures are such that the cells are really bathed in the things that they make, and they respond over time, and you capture that material at different time points. And most importantly, by adding immune cells to the devices, we're able to demonstrate that the inflammatory microenvironment that involves not just the somatic cells, but also the immune cell component, adds a different element to the device. And we can see that the immune system's interface with the endocrine system is really giving us the same readout that we were predicting from our in vivo studies.